Good morning students. Today is lecture 18th of module 6. In today's lecture, we will basically discuss about the nanofiltration. We will try to understand what is nanofiltration, and even I will tell you how nanofiltration and reverse osmosis overlaps each other and what is the difference between them. We will try to see also learn also what is the transport mechanism of nanofiltration systems and the various fouling models and the various applications of nanofiltration. So, as you know, nanofiltration refers to a specialty membrane process that rejects dissolved solutes in the approximate size range of 1 nanometer or 10 angstrom. So, very small size solutes are being rejected. With respect to the size and weight of solutes that nanofiltration membrane reject, nanofiltration operates in the realm between the reverse osmosis and ultrafiltration. So, actually based on the range of the solutes it rejects, the membranes are being classified. So, nanofiltration lies something somewhere between the cutoff of reverse osmosis and ultrafiltration. Hydraulic pressure is used to overcome the feed solution's osmotic pressure and to induce diffusion of pure water, which we also called as permeate through a semi permeable nanofiltration membrane. The residual feed stream referred to as the retentate, concentrate or reject is concentrated by the process. Now, nanofiltration membranes can effectively reject dissolved organics, endotoxins, pyrogens, insecticides, pesticides, herbicides, antibiotics, nitrates, sugars, latex emulsions, etc. And nanofiltration may achieve moderate to low removal of monovalent ions, for example, your sodium, potassium chloride, etc. An ideal nanofiltration membrane has a very high water permeability, right, and but the ideal permeability of solutes may be near 0 or some higher value depending on the solute and application. So, an ideal nanofiltration membrane will have as much as will pass as much as water or permeate as much as water, however retaining all sorts of solutes and ions. So, the features of nanofiltration lies between that of non-porous RO membrane and porous ultrafiltration membrane. This is what we just discussed. Commercial nanofiltration membranes possess a fixed charge developed by dissociation of surface groups such as sulfurated or carboxylic acids. So, you can see this particular figure here, that how nanofiltration is rejecting large molecules, small molecules and multivalent ions. However, the monovalent ions, because of very small size, are passing through the membrane along with water. Here this particular figure will tell you the operating range of the nanofiltration. You can see the pore size is 1 nanometer here. Okay. So, nanofiltration is ranged between here RO, here this is RO and this is ultrafiltration range. So, RO less than 1 nanometer mostly here, and UF greater than 1 nanometer, almost into the range of 10 nanometer and higher size. The properties of nanofiltration membranes therefore allow ions to be separated by a combination of the size and electrical effects of UF and the ion interaction mechanisms of the RO. So, that means note that the NF actually works in the combined principle of UF and reverse osmosis. So, UF basically is a size exclusion membrane process, as well as charge based separation also affects. However, in RO the ionic interaction plays a major role. So, in NF both all these things are playing a role while rejecting a solute or permeating the water. The size of pores in nanofiltration membrane is such that even small uncharged solutes are highly rejected, while the surface electrostatic properties allow monovalent ions to be reasonably well transmitted, while mostly retaining the multivalent ions. Now, if you look at that further properties and look at this particular schematic here, you can see this water and monovalent ions are mostly being transmitted or passed to the permeate side, whereas multivalent ions, most of the multivalent ions, viruses, bacteria, suspended solids, all are getting rejected. Some multivalent ions will of course pass through the membrane because of the various non ideal semi permeable membrane that is actually existed. So, NF membranes can be produced in platen frame form, spiral wound, tubular, capillary, hollow fiber formats from various membrane materials, mostly cellulosic derivatives. Maybe there are some synthetic polymers and there are inorganic materials also, ceramics also available. Now, NF can withstand very high or low pH environment. NF membrane tend to have a slightly charged surface with a negative charge at a neutral pH. Two types of transport theories or models are basically adapted to describe the nanofiltration transport. So, first one is the Sori-Rajan sorption surface capillary flow theory and the second one is the usual solution diffusion model, which we have discussed in detail in our previous classes. So, in Sori-Rajan sorption surface capillary flow theory, so actually it describes the preferential sorption of water molecules in the membrane and then the desorption of multivalent ions by dielectric forces, causing exclusion of charged solutes even smaller than the membrane pores from movement into the membranes. So, that means the membrane the water molecules are getting sorbed inside the membranes, okay. Then they are passing through the permeate side and that desorption of the multivalent ions are happening due to the dielectric forces, because as we just discussed that the membrane NF membranes are slightly negative in charge. So, smaller than the pore size of the membranes ions are also getting rejected. So, effective charge density, pore radius and ionic strength determine the rejection of monovalent ions. For nanofiltration membranes, the rejection of monovalent ions ranges between 0% to 50%. So, under solution diffusion, this we have discussed as I told you in detail earlier. It is the same for RO we have discussed. So, it describes the membrane as a porous film into which both water and solute ion dissolves. Whatever is getting water has to be served inside the membrane material and then only it will get into the permeate side. Similarly, the solute ions which are supposed to be transmitted through the membrane must dissolve itself in the membrane material. Then diffusion will take place. So, the solute moves in the membrane mainly under the concentration gradient forces. The water transport is dependent on the hydraulic pressure gradient. So, that means more you are giving supplying the delta P. So, more will be the water flow and the transport of the solute through the membrane depends on the hindered diffusion as well as convection. So, let us understand the transport mechanism of the charged solutes in NF. Transport of solutes through NF is more complex than any other membrane processes. Actually, three different modes of transport occurs. The first is diffusion, which is due to the concentration potential gradient as in the reverse osmosis membranes. Then convection as in the larger pore size filtration such as microfiltration or even ultrafiltration. Then electromigration. So, attraction and repulsion from charges within and near the membrane. So, you can see this particular image which was actually proposed or given by one of the paper in desalination by Yagnesani et al. So, this is the solute transport mechanisms occurring simultaneously for each ion. Now, the mechanism also depends upon the feed water and its composition. This is here of course, this is the membrane, right. So, active layer thickness given by delta x and the water flux and solute flux both are in this direction. So, you can see diffusion is ion movement due to concentration gradient. Okay. So, you can see this is given by this particular line. So, you can see the there is a concentration gradient at the downstream side. So, that is why movement of ions will happen through the diffusion. Then convection. So, ion movement with solvent flow. So, along with solvent, that means along with the water, some ions will also are flowing through. So, this indicates that the membrane are having some porous. So, they are porous, some pores are existing. Okay. Otherwise, if there are no pores, absolutely non-porous membrane, then convection will not happen basically. So, then there is electromigration. So, that means ion movement due to potential gradient. So, as we know that NF membrane is slightly negatively charged, you can see this, right, and then at the upstream side you are maintaining some positively charged. So, ion movement takes place by the flow of cations and anions in both ways. Now, ion movement will take place both ways. So, transport mechanism of charged solutes can be explained by three things actually. One is your Donan exclusion, the next is actually your dielectric exclusion, and then there is also something called a steric exclusion. So, we will learn what is all these things one by one. So, Donan exclusion, actually what is Donan exclusion? If you see the IUPAC actually definition, it says reduction in concentration of mobile ions within an ion exchange membrane due to the presence of fixed ions of the same sign as the mobile ions. So, that means you see the cation exchange matrix which are having this negatively charged ions already onto them. So, it will repel the same charge groups. Similarly, anion exchange membrane which are having this fixed positive charge will repel the positive charges, thereby attracting the opposite charge. So, this is, and then after some time some equilibrium will be observed here. So, that is actually called Donan equilibrium. So, Donan exclusion has a pronounced effect on the separation of nanofiltration compared to other pressure driven membrane processes, because we are mostly dealing with the ions, or each ions are having some charge. Due to the slightly charged nature of nanofiltration membrane, solutes with an opposite charge compared to the membrane are attracted. So, solutes with a similar charge are repelled. At the membrane surface, a distribution of co and counter ions takes place, thereby causing an additional separation. So, the next one is dielectric exclusion. Now, water molecules show a polarization in the pore due to the charge of the membrane and the dipole moment of the water. The polarization results in a decrease in dielectric constant inside the pore, thereby making it less favorable for a charged solute to enter. That means, when the water is getting polarized inside the pores, it is hindering the diffusion of solutes inside that pore. So, this is what is actually known as dielectric exclusion. So, even in a situation that the dielectric constant inside the pore equal to the one in water, a change in electrostatic free energy of the ion occurs when the ion is transferred from the bulk into the pores. So, this also results in exclusion. Now, let us see this particular figure again given by Yagneswala et al. In the desalination. This particular you can refer to this nice publication actually from where this material is taken. So, you can see this exclusion mechanisms occurring simultaneously for each ion. Steric exclusion. So, this is nothing but the size exclusion, then your dielectric exclusion, then your Donan exclusion. So, you can see this in steric exclusion, ion bigger than the pore opening. Okay. They are trying to they will be actually rejected on the surface of the membrane. So, exclusion means actually we are talking about rejection. Okay. How rejection is happening? On say rejection of solutes on the membrane surface is happening. Then dielectric exclusion, something like this it will happen. So, ion needs to shed hydrogen cell to enter the membrane. So, it is difficult because the membrane is already charged, some charge. Okay. Then there are counter ions will be there. So, they will try to form some group, something like this, some structure, something like this. So, thereby the rejection of the oppositely charged similar charged particles ions will happen. So, then your Donan exclusion. So, here the repulsion and expulsion happening due to the positive or negatively charged ions. So, membrane charge considering it is negative. So, we will see this how the repulsion is happening. Okay. So, this particular figure tells us the rejection mechanism of the charged solutes on the nanofiltration membrane. So, let us now understand the different parameters that affect the performance of a nanofiltration membrane. So, there are various parameters, we will see one by one. First one and foremost one is of course the pressure. So, pressure difference is the driving force responsible for a nanofiltration membrane. So, effective driving force is applied hydraulic pressure less the osmotic pressure that is applied on the membrane by the solutes. Okay. Temperature. So, nanofiltration membrane flux will increase with increase in temperature. Due to the reason is that when the temperature increases, the viscosity is reduced, that is why the flux getting enhanced. Then cross flow velocity. So, nanofiltration membrane flux increases also along with the increase in the cross flow velocity. Why? Because if there is a higher cross flow velocity, then what it will do is basically the feed itself will wash away the concentration polarization layer, or we can say that the deposition whatever is happening on the surface of the membranes will be washed away due to a higher flow rate. So, thereby reducing the concentration polarization as well as fouling. So, the maximum cross flow velocity depend on the mechanical strength of the membrane and construction of the element and system hardware. Operating a NF membrane at too high cross flow velocity may cause premature failure of the membrane and module. So, it is true that you cannot operate a NF system beyond a certain pressure, otherwise your system will failure and membrane will get rupture. So, the next other parameters are solution pH. So, you know solution pH is the one of the most important parameter whenever you talk about any liquid systems, okay, liquid phase systems, whether you are doing some separation, carrying out some reaction, whatever. So, charged sites on the NF membrane surface varied with pH. So, negatively charged at a neutral pH and lose their charge at acidic pH. So, most NF and RO membranes have lower rejection at low pH. Because their surfaces are already charged and mostly it is negatively charged at neutral pH. However, the pH dependency of a membrane is determined according to the chemistry applied to produce the membrane. So, let us understand the nanofiltration advantages. It has lower discharge volumes, lower retained concentrations than RO for low value salts, reduced salt content and dissolved solid content in brackish water, reduction in heavy metals, reduced nitrates and sulfates, reduction in color, tannins and turbidity, softens hard water with the use of specific softening membranes, chemical free, that is needs no salt or chemicals during the operation, and pH of water after nanofiltration is normally non-aggressive and disinfection. So, these are the things that is being done by the nanofiltration membranes. So, it has certain disadvantages also. So, higher energy consumption than ultrafiltration and microfiltration. So, almost 0.3 to 1 kilowatt per hour per meter cube. So, another important thing is that pretreatment is required for some heavily polluted water. So, prefiltration 0.1 to 2 microns, all these things needs to be removed, otherwise the your membrane will be clogged and it will not give the targeted performance. So, this is always the case with spiral wood membranes. Since spiral wood membranes are typically framed as a leaf, we have understood how spiral wood actually works during our membrane module discussion as well as in RO also. So, you know how it is being fabricated. So, the space in between is too less. So, they are more prone to fouling. So, it is important that there is a pre-treatment before nanofiltration. Okay, for heavily polluted, it is not that every water streams or feed water has to be pre-treated. So, limited retention for salts and univalent ions. Nanofiltration membranes are little more expensive than reverse osmosis membranes. So, membranes are sensitive to flea chlorine. So, most of the time chlorine is present in water and water streams. So, they are not very good chlorine resistance membranes. So, lifespan of around 1000 ppmh. Okay. So, an active carbon filter or a bisulfite treatment is recommended for high chlorine concentration. Let us understand the benefits of the NF water treatment. So, most of the times NF is actually used to produce potable water. So, in that case what are the advantages? So, the operating cost actually is very less, energy cost is also less, lower discharge and less wastewater than reverse osmosis, and that means it produces. Then reduction of total dissolved solids content of slightly brackish water, reduction of pesticides and volatile organic compounds, reduction of heavy metals, reduction of nitrate and sulfates, reduction of color, tannins and turbidity, hard water softening, being chemical free. So, it does not use any salts or chemicals. Water pH after nanofiltration is typically non-aggressive. So, NF applications includes desalination of food, dairy, beverage products or byproducts, partial desalination of whey, UV permeate or retentate as required, desalination of dyes and optical brighteners, purification of spent clean and place chemicals, CIP chemicals, color reduction or manipulation of food products, concentration of food, dairy and beverage products or byproducts, fermentation, byproduct concentration. Let us see one, this is one application in which nanofiltration membrane is used to produce your clean water, even for drinking water taps as well as other culinary applications. So, you can see the schematic here. So, the raw water is coming, as I told you that one of the disadvantage in nanofiltration is that it needs a pre-treatment, not always, but most of the times, depending upon what is your feed water composition and what it contains basically. So, then it goes to a through a pump, basically high, this is a high pressure membrane system pump, it is a high pressure pump. Okay. So, this high pressure pump will pump the raw water or filtered water to the nanofiltration system. So, you get a permeate and a concentrate. So, the permeate is goes to the purified water storage tank. Okay. Then it can be taken for the culinary or drinking water taps, or there is a purified water or it may be recycled back partly to maintain the volume. See, many times here also this may needs another finishing step. Now, this finishing step is basically required because most of the ions are devoid when we are doing the nanofiltration. So, it is actually when we are talking about a potable water system, for a potable water applications. So, you need to sometimes remineralize the NF water. So, the concentrate which is coming here and getting stored here. So, this concentrate is also can be used to toilets and other non-culinary application. Now, you can use it for watering your plants in the garden and all these things. So, even used in the toilets, many of the big hotels, star hotels are now doing are adopted this technology, and you will see this in the washroom. Many times it is written that especially in the this one in your commodes, you can see the color of the water is slightly greyish or little yellowish. So, it will be written that because this is treated water. So, there is some color. So, you can remove the color also completely, but it will unnecessarily add on the processed water cost. So, it is not required. So, whatever you are using for your bathing or drinking purposes or in the or washing, so you will get the you will obviously being supplied with the good water. So, another NF application is the purifying anion exchange resin regeneration effluent in the sugar industries. So, here what is happening actually, a combination of resin and membrane processes is especially attractive for plant locations where the waste disposal is a critical issue. Now, most of the industries that do not have land for waste disposal, and there are stringent rules of waste disposal also being imposed. So, it is imperative that they need to treat it. So, in the future NF is expected to find applications in the recovery of water and salt from waste brine at a sugar decolorization plant in sugar industry. So, these are also getting adapted nowadays. So, in addition, the volume of toxic wastes discharged from sugar refinery columns can be lowered. So, you can see how it is happening actually. So, this regenerant effluent, that is the air fresh is coming, and you are adding the decolorization agent. So, decolorization effluent is being taken here and regenerated effluent, okay, which is being stored here. So, this is basically your NF feed. So, it goes to the nanofiltration system where you are getting the concentrated regenerant, which is the NF retented to secondary post treatment or to drain. You can just use it again, as I told you, for watering garden and all these purposes, non-culinary purposes, and the NF permeate. Okay. So, this is nothing but the recovered regenerant brine tank goes and stored there. So, this will be recycled back. So, there is this is another application. This is a conceptual design for the fractionation of artichoke brine by integrated membrane process. Now, here this is a hybrid system, you can say. Okay. Usually we say hybrid system is something where two different unit operations are clubbed together. Okay. But here two different membrane systems are clubbed together. So, you can say it is an integrated membrane process. So, you can see here there is a ultrafiltration membrane, there is a nanofiltration membrane. Okay, why it is being used? So, let us try to understand. So, artichoke brine is stored here. See, artichoke brine is being fed to the ultrafiltration membrane. So, before it is being fed to the ultrafiltration membrane, some sort of pre-filtration happens to remove the floating solids, suspended solids, and certain other larger molecular weight compounds. So that the UF membrane will not, UF membrane being porous, it should not get clogged. So, this filtered artichoke brine then goes to the UF membrane, where we are getting the retentate. So, retentate is getting enriched with what? Suspended solids, higher molecular weight substances. Okay. Now, you try to understand that why we are using a UF here. If you do not use the UF here, directly feeding the artichoke brine after this pre-filtration, okay, to here, then all these whatever the UF is getting rejected will be rejected here, but the membrane performance will decrease drastically. Okay. So, that is why there is a need to actually pre-filter, as well as there is a need to place a UF, so that the UF will remove most of the suspended solids and the high molecular weight components. So, the permeate devoid of all these things, okay, and having only smaller molecular weight compounds and ions is being fed to the NF. So, the NF retentate is basically caffeinoquinic acids, flavonoids, etc., and this goes for the formulation for food or nutraceutical application. So, this is actually our product of interest, okay. And whatever the permeate is there, it is getting recycled here, okay. So, it is a salt solution mostly, right. So, and again being fed to the artichoke brine feed tank. So, the exhausted brines are submitted to a preliminary ultrafiltration step aimed to remove most of the suspended solid. This is what I already told you. So, the ultrafiltration permeate is a clear solution containing more than 90% of 5% of the compounds of interest. So, it takes out all the larger molecular weight components, as well as your TDS, most of the suspended solids. So, components which are smaller molecular components, this caffeinoquinic acids, flavonoids, etc. So, they will be fed back fed to the nanofiltration system. So, the subsequent treatment with spiral wood membrane of 300 Dalton, okay, allows to obtain a retentate fraction enriched in phenolic compounds and with a salt content able to stabilize the retentate itself. So, this fraction is of interest for food or nutraceutical applications. So, the NF permeate is a salt solution free from caffeinoquinic acid, which can be designed for reuse in the processing cycle or replenishing of fresh brines with a consequent reduction in the volume of water used in the process. So, this is another classic example of the bench scale cross flow NF setup, okay, for the treatment of oil sands produced water. So, you can see this, there is a feed tank, okay. So, then it is a high pressure pump is here. So, it is pumping the feed water to the nanofiltration membrane, where you are getting permeate here, okay, and then the retentate is again being fed back, or it can be taken out also. Okay. A typical system consists of a feed tank, a membrane cell, a pump, a temperature controller to keep the feed temperature at a specific value, a back pressure regulator, and a bypass valve to adjust the applied pressure and a cross flow velocity. So, a weighing balance is here, you can see this, or a digital flow meter are used to measure the permeate flow rate. Permeate and retentate are recycled to the feed tank to maintain a constant feed concentration over time. Another application, this is the dead end nanofiltration under constant pressure. You can see this is several types of viral removal devices, okay, are available as self contained and disposable capsules and cartridges that can be subjected to integrity tests. So, with such devices, protein solution can be filtered in a dead end flow filtration mode under a constant pressure mode, as you can see. So, you can see this is your NF system here actually, okay. So, the protein solutions are getting actually filtered here, okay. So, you are getting the receiving flash here, the test tube, whatever the permeate can be collected here. So, let us now understand the nanofiltration fouling mechanisms and the models. So, the water flux in RO and NF can be expressed as ZW equals to delta P minus delta pi by R tot or R TOT. So, here ZW is the water flux, delta P is the applied pressure difference, delta pi is the osmotic pressure difference, and R tot is the total resistance. Okay. Now, the total resistance of the membrane is composed of 3 separate resistances in series. Okay. So, Rm, Ri and Rf. So, Rm is the resistance of a clean membrane to permeation of clean water and it is time independent. Okay. So, Ri is initial fouling resistance caused by concentration polarization and fouling of the membrane and it is time independent. Okay. Rf is time independent fouling resistance. So, you can write this actually R we can write R of total. So, in series we can write R m plus 1 over R I plus 1 over R f. This is how you write actually this one the resistances. Von Boxtel correlated I empirically with a cross flow velocity, upstream pressure and concentration ratio and proposed this particular equation. So, R I equals to A V to the power of B, P to the power of C and C R to the power of D. So, C are actually concentration ratio. So, A, B, C, D are the empirical constants. For example, why this is being necessary and we are talking about this actually and fouling problems also becomes very severe. So, for example, we are taking a fermentation broth. So, fouling becomes a major issue when we are dealing with a fermentation broth as it contains salts, colloidal particles, bacterial cells, proteins which may cause fouling. Most of them are biofoulants. So, by treatment of fermentation broth by ultrafiltration, protein, bacteria can be removed and fouling properties of the solution can be changed, thereby reducing the overall resistance also. Then against it can be sent to the nanofiltration system. So, a fouling model can be expressed by this particular equation in the terms of Rf. So, drf dt equals to A into Zw minus B. So, Rf at t equals to 0 equals to 0, that means Rf at time 0 equals to 0. So, where A is given by epsilon Cbpr by rho and B equals to B is given by this particular equation. So, where epsilon is the specific gel layer resistance, Cbpr is the protein concentration in the bulk, Cgpr is the protein concentration in the gel and Kpr is the mass transfer coefficient of protein in the boundary layer. Now, the above equation predicts the flux dependent increase of Rf with time and can only be applied with a constant Cbpr as in a continuous system. So, in case of a changing Cbpr that occurs during batch wise concentration of solutions, the above equation can be transferred into this particular equation where drf by dt equals to Cr into A into Zw minus this particular equation a term minus ln Cr. So, where Cr is given by this equation V naught by V naught, then integration of this Zw Aw dt. So, if proteins are absent as in ultrafiltered fermentation broth, the gel layer model cannot be applied because it is not required this because there will be no gel formation on the membrane surface. So, a precipitation model or a colloidal fouling model is more appropriate in this situation. So, Cohen and Probstein developed a model in which deposition of colloidal particles caused fouling. So, they discovered that colloidal fouling was convention controlled and using the law of mass conservation they derived a equation is given below. So, drf by dt equals to this phi naught Zw naught Rc by 1 minus epsilon c. So, where phi naught is the foulant volume fraction in the feed, Zw is the water flux determined by extrapolating the flux time versus curve to time to 0. Okay. So, basically it is the flux at 0. So, epsilon c is the effective foulant layer resistance and this model shows that the increase in long term fouling is constant linearly dependent on the foulant volume fraction. So, for a given feed which is processed at different Cr and when it is assumed that Zw naught shows the same pressure dependence, the above equation can be transferred into drf by dt equals to d by Rw naught Cr delta p minus delta pi, where d equals to this phi naught Rc into 1 minus epsilon c. So, Rw naught is the resistance at intercept of the flux time curve at time equals to 0. So, the RWO put into the concept of initial and long term fouling is equal to the sum of Rm and Ri. By performing experiments at different Cr and delta p, the first factor on the right hand side of the above equation can be evaluated. The factor D should be independent of the process condition. In the case of batch wise concentration, the assumption of a quasi steady state flux made by Cohen and Probstein does not hold. For this case, Zwo in the above equation is replaced by ZW. So, let us see this particular figure here. So, this is a resistances as a function of time of a continuous experiment with a UF broth and a only broth. Okay. So, UF broth means ultrafiltered broth. Okay. So, an example of a continuous experiment with lactic acid fermentation broth is shown here. So, it is clear that during continuous NF of the UF broth, Ri is the largest resistance. So, this is the UF broth, this is UF broth, this is UF broth, this is UF broth, and this is for Ri, this is for Rm, this is for Ri. Okay. You can see this is for Rm, this is for Rf. So, you can see this. So, it is clear that during this the nanofiltration of the ultrafilter broth, Ri is the largest resistance, by value you can see. Okay. So, time dependent fouling Rf hardly contributes to the overall resistance of the water permeation. So, Rf is almost negligible. So, you can almost neglect the Rf. Okay. Now, this shows that osmotic effect and concentration polarization effects during continuous NF and UF broth cause the main mass transfer resistance. Okay. So, NF membrane and module. So, there are two types of membranes actually available commercially, the spiral wound and the tubular membranes. So, spiral membranes are cheapest but more sensitive to pollution. Tubular and straw membranes, the most used membranes in the costs and effect, shall not easily be polluted. The surfaces from the filter determine the capacity from the filter. Spiral membranes have the biggest surface area in general and are therefore most cheapest in use. The surface area from tubular and straw membranes is usually less in general. So, the pre-purifying of the feed water has an influence on the performance of the installation. The need of pre-purifying depends on the feeding water quality. So, let us now try to understand before we wind up what is the difference between RO and NF. So, you know that we have discussed this, that RO and NF are they are very much similar to each other, but they can be distinguished based on the size of the particulate or solute that each is able to remove or reject. So, comparatively RO and NF are capable of removing finer contaminants than microfiltration and ultrafiltration, with applications including removal of hardness, that means the scale formation scale forming components, nitrate sulfates, TDS, heavy metals, radionuclides and organic macromolecules from process waste and waste streams. So, RO, this is just this tabular format to try to understand the differences. So, RO is rejecting a small, they are having small pores. So, they are capable of removing particles as small as 0.1 nanometer, whereas NF range is almost 0.0022 to 0.005 microns. Okay. So, RO is a age old technique existing almost since 1950s. However, NF is a very recently developed technology. So, RO was used cheaply for the or mainly for the desalination purposes, as in potable water generation from seawater or brackish water sources, and NF is exclusively developed mainly for the potable water generation. So, RO is extremely efficient in removing all ions, large or small, and NF will remove harmful contaminants such as pesticide compounds and organic macromolecules, while retaining minerals that RO would otherwise remove. So, nanofiltration membranes are capable of removing larger divalent ions such as calcium sulfate, while allowing smaller monovalent ions such as sodium chloride to pass through. So, this is a technical assessment of the NF technology. So, you can just go through it. So, the status of technologies, it is NF at present is quite mature and it is a robust technology. So, applications are wide. The most of the important applications are water softening, metal removals and produced water treatment. The feed water quality, it handles almost 500 to 12,000 milligrams per liter of TDS. Okay. And product water quality, that depends of course on the feed water quality and operating conditions. However, greater than 90% rejection of larger divalent ions and metals are possible. Moderate rejection of monovalent ions are possible in nanofiltration. So, recovery range is almost 75% to 90%. This is one of the most important parameter when you talk about industrial applications. Then pre-treatment of feed water is necessary, as we have learned in today's lecture. So, it is required so as to reduce scaling as well as fouling. post treatment of product water sometimes require, especially we are talking about potable water, because it is devoid of all sorts of minerals. So, remineralization to maintain sodium adsorption ratio, that is the SAR value, is actually required. So, energy use is quite less than the RO for the same feed water quality. There is no chemical use, however, sometimes we use anti-scaling and anti-fouling inhibitors. Okay. And this basically the caustic and some polymers may be, and the lifetime depends actually. So, it is all any time between 3 to 7 years, depending on of course the use and the operating conditions. So, thank you very much. So, today's lecture mostly is taken from Professor Nath's book as well as some other journal sources. Okay, please go through it, and in the next class we are starting ultrafiltration in the next module. So, we will try to understand the basic principles and advantages of ultrafiltration, different types of membranes and modules that is required for the ultrafiltration, and various types of ultrafiltration configurations. So, thank you very much. In case you have any query, please feel free to write to me at kmohanty@iitg.ac.in. Thank you.